I'm Zhao Shuai, a PhD student from Tsinghua University. Today my presentation is about a wearable anemometer for two-dimensional wind detection. First, I will introduce the background and then go to the detection principle, design, and fabrication of our sensor. And next is the two-dimensional wind detection, and finally is a summary. Wearable devices are very popular now, and I think maybe the most important function of wearable devices is to acquire information. The information includes the information from the internet, from our friends, and from ourselves, such like physiological signals and our body movement. Besides, I think it also should include the information from the environment, such like the sound, light, and wind. Wind detection plays an important role in agriculture and weather prediction. So traditionally, we use this mechanical anemometer to detect wind. So we want to make wind detection to be wearable. In this way, I think it will facilitate our outdoor sports and field works. And maybe if we can detect wind by our wearable devices, maybe we don't need this big weather station, because everyone will be a little weather station. So by gathering the information from the devices, we can get a more precise wind map, and it's a more low-cost method. So the key factor is how to detect two-dimensional flow detection. Microthermal sensors are studied for two-dimensional flow detection because it has the advantages of high sensitivity and faster response. In this design, heater is in the center of the sensor, and its temperature distribution could be changed by the flow, and it can be detected by the around detectors, so we can know the flow information. But the motivation of our work is that small anemometer for wearable applications. So we wish that the sensor could have a more simple structure, and it should have a low power consumption. And maybe if the sensor could have a flexible structure, maybe it could adapt to the potential curved surface of the anemometer shell design. So we propose a compact sensor that uses hot film elements that serve as both of the heater and the temperature detector. The basic principle of hot film flow sensor can be seen in this figure. The hot film is made of a thermal-resistive material, so its resistance is related to its temperature. So when it works, it will be electrically heated to a higher temperature, and when an external flow passes, its convective heat transfer between the hot film and the flow will be enhanced, and its temperature will be decreased. So we can know the flow rate information by measuring its resistance. So if we have two hot film elements, because the heat transfer is different between the upstream side and the downstream side, so we can know besides the flow rate, we can also know the flow angle, but we can only know the angle is 0 degree or 180 degree. So if we have three hot film elements, theoretically we can know the flow angle from 0 degree to 360 degree. Considering the uniformity, we think the circle design is a better choice. So if we divide a circle into three sectors by the combination of the three elements, we can extract the flow rate and the flow angle together, and so this is the detection principle of our sensors. Next, this figure is the layout of our microsensor, and the three elements are located in a circle with a diameter of 2 millimeters. The fabrication process is very simple. Only one lift-off process is needed, and we fabricated the sensor on a flexible polyimide. So the sensor is is a micro and flexible sensor, and as a result, it also has a compact design and a simple fabrication process. So it will meet the demand for wearable application. Then the structure of our wearable anemometer can be seen in this figure. We use the constant temperature difference circuit to operate the sensor. This mode circuit has a high sensitivity, and we also integrate a Bluetooth module into the anemometer, so it could be a wireless connection. And we also put a battery into it. This is the two-dimensional wind detection result. We changed the flow velocity and the direction angle together, and the output voltages of the three elements is shown in the figure. We can see that the output voltages of the three elements increases with the flow velocity, and under a constant velocity, this purple here, the output voltage and the direction angle meets a cosine relationship. Of course, there is a phase difference of 120 degree among the three elements. By the combination of the three output voltages of the elements, we can extract the flow velocity and the direction angle together. In our previous work, we use neural network to extract the two parameters. For wearable applications, we think the algorithm should be as simple as possible. So we propose a simplified algebraic method to extract the two parameters. This will reduce the calculation, and it's an effective method. X is the result. The top figure is the measured velocity versus actual velocity, and the bottom figure is the measured angle versus actual angle, and the insets are the errors. As a result, our anemometer has a flow velocity measurement range from 2 to 20 meters per second, with an error of 0.44. And the direction angle measurement range is 0 to 360 degree. The error is 2.15 degree. We also test the response time. It's about 0.5 seconds, and the power consumption is 100 milliwatt. The battery we use is a Li battery with 3.7 volt and 100 milliampere hour, so it could continuously working longer than 3 hours in our wearable anemometer. So to display the detection result more conveniently, we also developed an Android app. The smartphone could acquire the data from the anemometer by Bluetooth, and the two flow parameters could be extracted by the signal process algorithm, and the detected results could shown in this app. The direction angle can be indicated by the checking arrow. As a demonstration, we record this video. We use an electric fan to generate the flow, and we will move it to change the direction angle. this is the detection result. We can know that it can be it's the same with the movement. So the direction angle measurement, direction angle measurement is from 0 degree to 360 degree. So and finally is my summary. We propose a wearable anemometer for detecting two-dimensional wind velocity and direction angle. It's a small wireless anemometer and with a low power consumption. Our sensor is a flexible sensor, and it could be fabricated with a simple process, and so it would be a low cost. We also propose a simplified algorithm for wearable applications. I think it will find potential applications in personal electronics for outdoor activities and field works. And maybe it could be used for distributed measurement in meteorological monitoring and agricultural production. That's all the presentation. Thank you.